Now that we have talked about how processes actually create new processes, spawn new children, let's talk a bit about I/O, the input-output interface for the different processes. Uh, as you know, a computer is not just the CPU. I mean, we might overstate what we do in the CPU and in the memory in this course, but I mean, the computer is much more than this. You have your mouse, your keyboard, your monitor, your network card, your gaming console, and so on. And each of these devices is very unique. So your keyboard and your mouse are very different from, for example, your screen. They even have different specifications. I mean, keyboard requires to send in one character at a time, versus a monitor, which basically requires to receive, well, the data that will be that can be multiple characters, mostly multiple characters, multiple colors, multiple pixels, what goes where, and so on and so forth. So the size of data expected from for the different I/O devices is very different. And basically my camera right now, I mean, this is something that is recording videos which, well, are a few megabytes per minute, versus basically my mouse, which basically says that this is the differential movement between where the mouse was and where it should be. So I mean, they're very different in nature. One way to handle the input output for the different processes and for the computer is basically to have an interface per device, which would basically require that your different processes will call different interfaces for different devices. So for uh, if I have a process right now, which is, well, the OBS software that I'm using to record video and to basically show my screen and to show also my mouse movement and to record my sound, then this requires an interface per everything that the OBS software uses, and you will need an interface per device basically. And you can extrapolate from this because, for example, my mouse is a very special mouse. I can actually show you my mouse. It's this is my mouse. I mean, no, but very few people have such mice. It comes with, I don't know how many. I said 15 buttons last time. I think it comes with 15 buttons. Yes, and that basically makes it, well, not conventional, non-conventional in many ways. So if you have different models, I mean, your my mouse, since it's different from your mouse, then we should basically have different interfaces, different for even different mice. And, well, this was the way that things were done. That in the early computer days, I mean, in the 60s and the 70s, and, well, probably also sometime in the 80s, where basically there were very few companies that were making computers, and portability was not really an issue because you wanted people to be locked in to your device, to your computer, and that basically resulted into having a complete mess when it comes to portability. Actually, one of the companies that pushed towards the portability and the kind of easiness that we see right now in using computers was actually Microsoft, and this is one of their great achievements actually, because before that it was just a mess. So the way that Linux deals with the device problem, with the I/O problem, is that it builds a uniform interface, and this was an idea from Unix, which basically got captured by almost all operating systems that we know of today, and that's basically you have one single common interface for all devices and even for inter-process communication. So I mean, even if you have different processes that need to communicate on your computer, they use the same interface, and that is a very simple interface with open, close, read, and write. And the way that open works, for example, and the way that close works, for example, is very dependent on the hardware that you are trying to communicate with, right? So the definition of open, when it comes to basically opening uh, a new file, is very different from the definition of open when it is trying to communicate to the screen, for example, right? But it's from an application point of view, it's exactly the same. It's the same interface. So you can just think of it as open, close, read, and write as a programmer. And what open does is that it returns a handle or a file descriptor for use in later calls. Basically, when you call the screen multiple times, for example, then you will just need the file descriptor, which is kind of, if you're an object-oriented programming guy, then it's basically like you have initialized your object, basically. And open, close, read, and write are all byte-oriented. You have kernel buffers for read and writes for stream reads, for example. So everything gets buffered so that you as a programmer or the application basically sees the data coming from the screen or the data coming from the mouse or the data coming from my keyboard as basically block reads. So it collects things into a buffer and gives you a chunk of data, and this is the data that you need to actually think about. Okay, just need to shut that down. And that basically also has the effect of masking the different write read speeds of different devices. I mean, your CPU can read in, well, nanoseconds almost, right? Versus your hard disk, which has mechanical things rotating and cannot really do anything better than in milliseconds or microseconds, well, milliseconds mostly. Okay, so the difference in the speeds are masked by having buffers. So if you are a very fast device, then you wait until the buffer is filled, and then you read into a block, a chunk of data. And that means that if you are a very fast device, like if you are the CPU, basically, you can actually operate in such a way that you run for some time doing something else until the buffer gets filled, and then when the buffer gets, when you can read the block, you go read the block, operate on it very fast, and then go back to another thing. And then one of the important things is that you need an explicit close. So you need to close your connection to basically garbage collect any open file descriptors, so that you do not have open files that are supposed to be interfacing with different IOs, for example, while doing nothing. And I can give a very practical example of this. So right now I am recording using one of the programs that it's called OBS basically, and it captures the video from my camera, right? If I try right now to do a Skype video call, I will not be able, or the other party will not be able to see me, because right now there is an open file descriptor that basically blocks the camera to OBS. But if I shut down the program, or if I basically explicitly close the this connection to my camera, then I can basically come back and make new video calls. Okay? And as we said, open and close and read and write are Swiss knives. So open returns just a file descriptor, and then what does that do is very dependent on in which context we are talking about open. So if I ask you what does open do in a very, very general context, besides making a file descriptor, you cannot basically say anything. Because, for example, if file does not exist, you can return an error. Okay. If file does not exist, you can create file and open it. With the same open command. If file does exist, you can return an error. If file does exist, you can open file. If file exists but is not empty, nix it, then open. If file exists but is not empty, return an error. So these are all different and various basically natures of open. And the question can be basically, when is when? So basically, when does open behave like this? When does it behave like that? Can you think of examples when open behaves in these different ways? Okay, so Unix pipes. I mean, you have dealt with Unix pipes, and that's basically the buffering part that we have been talking about. You basically have a producer and a consumer, and the producer is one of the devices that writes to a buffer, and the consumer is one of the devices that reads from the buffer. And this is basically the continuation of the open, close, read, write. And you have a buffer that basically buffers stuff based on the speed um, of your devices. Then this buffer gets filled either faster than it's read or slower than it's read. And if the buffer gets filled faster than it's read, then it's problem. It is a problem, right? So if you then you get performance loss, because what happens is that the producer is producing a lot more data than the consumer can actually consume, and then the buffer gets overfilled and you lose data. But typically, I mean, things writing to these buffers are typically slower. So you have the CPU, which is absolutely the fastest thing on your computer, that typically consumes this data from the kernel buffer. And the pipe gets terminated once either endpoints close the pipe or exit. So, I mean, if you no longer are reading from the buffer, then basically there is no need to produce stuff, and vice versa. If you're no longer producing anything, then there is no need to actually watch the buffer. So you basically this is the read and write processes in Unix when it looks when you look at, like, for example, Unix pipes, and this is what Unix pipes kind of do also. So also this is quite similar to the client server model, where you basically have a client and a server. The client is typically reading or writing. I mean, let's talk about, for example, a web server as a server. And the web server contains data, for example, your Cambro or your scalable learning accounts, and you are basically trying to read stuff from there, and that's from maybe the videos or the slides, the lecture slides. So you're trying to read them, and when you read them, basically the server puts them in a buffer and you read through that buffer. But you might also be writing, like answering the questions that we pose, or writing notes, or writing feedback on Cambro, and so on and so forth. And then basically there's a buffer also that writes before it writes to the server. And that's basically to have enough data to process. So, as I've already talked, that the Linux philosophy is what is called is very different from what we call microkernels. The Linux philosophy is called monolithic kernels, and they are the most widely used operating systems on Earth because, well, both Linux and Windows are monolithic, and that basically means that lots of functionality goes inside the operating system. Some people argue that, well, we are not using monolithic kernels, we are using a hybrid between monolithic and microkernels, but this is by definition not true, because a microkernel is supposed to be a minimalistic kernel, a very small kernel, and I mean, from a very theoretical point of view, it should be a few thousand lines of code, not a few million lines of code, because it just operates on the very basics that a kernel needs. Versus most of the kernels that we are using, most of the operating systems that we are using, which have a few million lines of code, which are basically Linux, Windows, and the likes. So they are not really, they cannot really, I mean, I do not believe, well, let me put it that way. I do not believe that you can call them hybrid, but a lot of researchers, I mean, the top people in the field, believe that you can call them hybrid. But one of the most philosophical people on this is Tannenbaum, and he does not believe that there is anything such as a hybrid between a monolithic system and a microkernel. So monolithic kernels, they are the most widely used. lots of functionality goes inside the operating system, and there are two central ideas in monolithic kernels. The first one is that you have a hardware abstraction layer, a HAL, and a dynamically loaded device drivers. Okay, and the HAL is basically a portable interface to machine-specific operations. So you have the hardware abstraction layer has two sides. The top side, which is basically talking to the kernel, should not change. This is basically very fixed, very stable. And the bottom part, which basically talks to the actual hardware, is what changes based on the hardware that you're running on. And that basically means, for example, when you're running on an ARM processor, an ARM64 processor versus an x86 processor, you will have the same top layer of the hardware abstraction layer to which the kernel actually communicates, but you'll have a different layer for the x86 for different architectures in the x86, for example. So if you have an old generation i7 versus a new generation i7 versus an ARM64 processor and so on. And this also, I mean, this is pretty natural since you have different hardware capabilities for different processors. Some processors, for example, come with what is called a co-processor that helps the processor in doing some stuff, or a floating point processor, and so on and so forth. And you always change the lower level of the HAL instead of everything, and instead of basically changing everything in the kernel. And when you do that, of course, you need to recompile, you need to flush your new operating system on your hardware.